Contact mechanics is the study of the deformation of solids that touch each other at one or more points. This can be divided into compressive and adhesive forces in the direction perpendicular to the interface, and frictional forces in the tangential direction. Frictional contact mechanics is the study of the deformation of bodies in the presence of frictional effects, whereas frictionless contact mechanics assumes the absence of such effects. Frictional contact mechanics is concerned with a large range of different scales. At the macroscopic scale, it is applied for the investigation of the motion of contacting bodies. For instance, the bouncing of a rubber ball on a surface depends on the frictional interaction at the contact interface. Here the total force versus indentation and lateral displacement are of main concern. At the intermediate scale, one is interested in the local stresses, strains and deformations of the contacting bodies in and near the contact area. For instance, to derive or validate contact models at the macroscopic scale, or to investigate wear and damage of the contacting body's surfaces. Application areas of this scale are tire-pavement interaction, railway wheel-rail interaction, roller bearing analysis, etc. Finally, at the microscopic and nanoscales, contact mechanics is used to increase our understanding of tribological systems, e.g., investigate the origin of friction, and for the engineering of advanced devices like atomic force microscopes and MEMS devices. This page is mainly concerned with the second scale, getting basic insight in the stresses and deformations in and near the contact patch, without paying too much attention to the detailed mechanisms by which they come about. History. Several famous scientists and engineers contributed to our understanding of friction. They include Leonardo da Vinci, Guillaume Montans, John Theophilus de Sagaliers, Leonhard Euler, and Charles-Augustin de Coulomb. Later, Nikolai Pavlovich Petrov, Osborne Reynolds and Richard Strybeck supplemented this understanding with theories of lubrication. Deformation of solid materials was investigated in the 17th and 18th centuries by Robert Hooke, Joseph Louis Lagrange, and in the 19th and 20th centuries by D'Alembert and Timoshenko. With respect to contact mechanics, the classical contribution by Heinrich Hertz stands out. Further, the fundamental solutions by Boussinesq and Cerruti are of primary importance for the investigation of frictional contact problems in the elastic regime. Classical results for a true frictional contact problem concern the papers by F.W. Carter and H. Fromm. They independently presented the creep versus creep force relation for a cylinder on a plane or for two cylinders in steady rolling contact using Coulomb's dry friction law. These are applied to railway locomotive traction, and for understanding the hunting oscillation of railway vehicles. With respect to sliding, the classical solutions are due to C. Catania and R.D. Mindlin, who considered the tangential shifting of a sphere on a plane. In the 1950s, interest in the rolling contact of railway wheels grew. In 1958, K.L. Johnson presented an approximate approach for the 3D frictional problem with Hertzian geometry, with either lateral or spin creepage. Among others, he found that spin creepage, which is symmetric about the center of the contact patch, leads to a net lateral force in rolling conditions. This is due to the fore-aft differences in the distribution of tractions in the contact patch. In 1967, Joost Kalker published his milestone PhD thesis on the linear theory for rolling contact. This theory is exact for the situation of an infinite friction coefficient, in which case the slip area vanishes, and is approximative for non-vanishing creepages. It does assume Coulomb's friction law, which more or less requires clean surfaces. This theory is for massive bodies such as the railway wheel-rail contact. With respect to road-tire interaction, an important contribution concerns the so-called magic tire formula by Hans Pacicar. In the 1970s, many numerical models were devised, particularly variational approaches, such as those relying on Duvort and Lyon's existence and uniqueness theories. Over time, these grew into finite element approaches for contact problems with general material models and geometries, and into half-space-based approaches for so-called smooth-edged contact problems for linearly elastic materials. Models of the first category were presented by Larsen and by Riggers. An example of the latter category is Kalker's contact model. A drawback of the well-founded variational approaches is their large computation times. Therefore, many different approximate approaches were devised as well. Several well-known approximate theories for the rolling contact problem are Kalker's FASTSIM approach, the Schoenheddrich-Elkins formula, and Pollock's approach. More information on the history of the wheel-rail contact problem is provided in Nother's paper. Further, Johnson collected in his book a tremendous amount of information on contact mechanics and related subjects. With respect to rolling contact mechanics, an overview of various theories is presented by Kalker as well. Finally, the proceedings of a CISM course are of interest, which provide an introduction to more advanced aspects of rolling contact theory. Problem formulation. Central in the analysis of frictional contact problems is the understanding that the stresses at the surface of each body are spatially varying. Consequently, the strains and deformations of the bodies are varying with position too, and the motion of particles of the contacting bodies can be different at different locations. In part of the contact patch, particles of the opposing bodies may adhere to each other, whereas in other parts of the contact patch relative movement occurs. This local relative sliding is called microslip. This subdivision of the contact area into stick and slip areas manifests itself in fretting wear. Note that wear occurs only where power is dissipated, which requires stress and local relative displacement between the two surfaces. The size and shape of the contact patch itself and of its adhesion and slip areas are generally unknown in advance. If these were known, then the elastic fields in the two bodies could be solved independently from each other and the problem would not be a contact problem anymore. Three different components can be distinguished in a contact problem. First of all, there is the deformation of the separate bodies in reaction to loads applied on their surfaces. This is the subject of general continuum mechanics. It depends largely on the geometry of the bodies and on their material behavior. Secondly, there is the overall motion of the bodies relative to each other. For instance, the bodies can be at rest or approaching each other quickly, and can be shifted or rotated over each other. These overall motions are generally studied in classical mechanics, see for instance multibody dynamics. Finally, there are the processes at the contact interface. Compression and adhesion in the direction perpendicular to the interface, and friction and microslip in the tangential directions. The last aspect is the primary concern of contact mechanics. It is described in terms of so-called contact conditions. For the direction perpendicular to the interface, the normal contact problem, adhesion effects are usually small and the following conditions are typically employed. The gap between the two surfaces must be zero or strictly positive. The normal stress acting on each body is zero or compressive. Mathematically, here are functions that vary with the position along the body's surfaces. In the tangential directions, the following conditions are often used. The local shear stress cannot exceed a certain position-dependent maximum, the so-called traction bound, where the magnitude of tangential traction falls below the traction bound. The opposing surfaces adhere together and microslip vanishes. Microslip occurs where the tangential tractions are at the traction bound. The direction of the tangential traction is then opposite to the direction of microslip. The precise form of the traction bound is the so-called local friction law. For this, Coulomb's friction law is often applied locally, with the friction coefficient. More detailed formulae are also possible, for instance with depending on temperature, local sliding velocity, etc. Solutions for static cases. Rope on a bollard. The capstan equation. Consider a rope where equal forces are exerted on both sides. By this the rope is stretched a bit and an internal tension is induced. The rope is wrapped around a fixed item such as a bollard. It is bent and makes contact to the item's surface over a contact angle. Normal pressure comes into being between the rope and bollard, but no friction occurs yet. Next, the force on one side of the bollard is increased to a higher value. This does cause frictional shear stresses in the contact area. In the final situation, the bollard exercises a friction force on the rope such that a static situation occurs. The tension distribution in the rope in this final situation is described by the capstan equation, with solution. The tension increases from on the slack side Catania problem. Consider a sphere that is pressed onto a plane and then shifted over the plane's surface. If the sphere and plane are idealized as rigid bodies, then contact would occur in just a single point, and the sphere would not move until the tangential force that is applied reaches the maximum friction force. Then it starts sliding over the surface until the applied force is reduced again. In reality, with elastic effects taken into consideration, the situation is much different. If an elastic sphere is pressed onto an elastic plane of the same material, then both bodies deform, a circular contact area comes into being, and a normal pressure distribution arises. Also, the center of the sphere is moved down a bit by a distance that is called the approach, which is also the maximum penetration of the undeformed surfaces. For a sphere of radius and elastic constants, this Hertzian solution reads. Now consider that a tangential force is applied that is lower than the Coulomb friction bound. The center of the sphere will then be moved sideways by a small distance that is called the shift. A static equilibrium is obtained in which elastic deformations occur as well as frictional shear stresses in the contact interface. In this case, if the tangential force is reduced, then the elastic deformations and shear stresses reduce as well. The sphere largely shifts back to its original position, except for frictional losses that arise due to local slip in the contact patch. This contact problem was solved approximately by Catania using an analytical approach. The stress distribution in the equilibrium state consists of two parts. In the central, sticking region, the surface particles of the plane displace over to the right, whereas the surface particles of the sphere displace over to the left. Even though the sphere as a whole moves over relative to the plane, these surface particles did not move relative to each other. In the outer annulus, the surface particles did move relative to each other. Their local shift is obtained as this shift is precisely as large such that a static equilibrium is obtained with shear stresses at the traction bound in this so-called slip area. So, during the tangential loading of the sphere, partial sliding occurs. The contact area is thus divided into a slip area where the surfaces move relative to each other and a stick area where they do not. In the equilibrium state, no more sliding is going on. Solutions for dynamic sliding problems. The solution of a contact problem consists of the state at the interface plus the elastic field in the body's interiors. This solution depends on the history of the contact. This can be seen by extension of the Catania problem described above. In the Catania problem, the sphere is first pressed onto the plane and then shifted tangentially. This yields partial slip as described above. If the sphere is first shifted tangentially and then pressed onto the plane, then there is no tangential displacement difference between the opposing surfaces and consequently there is no tangential stress in the contact interface. If the approach in normal direction and tangential shift are increased simultaneously, then a situation can be achieved with tangential stress but without local slip. This demonstrates that the state in the contact interface is not only dependent on the relative positions of the two bodies, but also on their motion history. Another example of this occurs if the sphere is shifted back to its original position. Initially there was no tangential stress in the contact interface. After the initial shift, microslip has occurred. This microslip is not entirely undone by shifting back. So in the final situation, tangential stresses remain in the interface. in what looks like an identical configuration as the original one. Solution of rolling contact problems. Rolling contact problems are dynamic problems in which the contacting bodies are continuously moving with respect to each other. A difference to dynamic sliding contact problems is that there is more variety in the state of different surface particles, whereas the contact patch in a sliding problem continuously consists of more or less the same particles. In a rolling contact problem, particles enter and leave the contact patch incessantly. Moreover, in a sliding problem, the surface particles in the contact patch are all subjected to more or less the same tangential shift everywhere, whereas in a rolling problem the surface particles are stressed in rather different ways. They are free of stress when entering the contact patch, then stick to a particle of the opposing surface, is strained by the overall motion difference between the two bodies, until the local traction bound is exceeded and local slip sets in. This process is in different stages for different parts of the contact area. If the overall motion of the bodies is constant, then an overall steady state may be attained. Here the state of each surface particle is varying in time, but the overall distribution can be constant. This is formalized by using a coordinate system that is moving along with the contact patch. Cylinder rolling on a plane. The Carter-From solution: consider a cylinder that is rolling over a plane under steady conditions, with a time-independent longitudinal creepage. Far away from the ends of the cylinders, a situation of plane strain occurs and the problem is two-dimensional. If the cylinder and plane consist of the same materials, then the normal contact problem is unaffected by the shear stress. The contact area is a strip, and the pressure is described by the Hertz solution. The distribution of the shear stress is described by the Carter-From solution. It consists of an adhesion area at the leading edge of the contact area and a slip area at the trailing edge. The length of the adhesion area is denoted. Further, the adhesion coordinate is introduced by. In case of a positive force, it is. The size of the adhesion area depends on the creepage, the wheel radius and the friction coefficient. For larger creepages such that full sliding occurs,